Hello and welcome. I'm Robert Neild. This is my channel, Many Mysteries, One Secret Solution. Please see the trailer for an overview of the entire video series, which will eventually cover more than 60 individual topics. This video, the first in the series, appropriately concerns the oldest of the mysteries, the question of how the pyramids at Giza were built. Standing on a limestone plateau above the Nile's west bank near Cairo, the main pyramids at Giza are named for the three generations of kings that built them: Khufu, the largest, on the right, Khafre in the middle, and Menkaure on the left, the smallest. The necropolis was constructed during the 4th dynasty of the Old Kingdom, starting with Khufu around 2580 BCE and ending with Menkaure around 2500 BCE. The upper part of Khafre's pyramid still retains the Tura limestone facing that originally covered all three pyramids. But down the centuries, the Tura limestone, because it was high quality, was taken and used for building material in Cairo. This photograph shows how the urban sprawl of Cairo, the city of 1,000 minarets, founded in 969 CE, has encroached on the Giza plateau. When the pyramids were built, however, the capital city of Egypt was at Memphis, about 15 miles to the south on the Nile's west bank. Giza represents both the final era and the zenith of pyramid building, which had begun a few hundred years earlier with simple mastabas that gradually evolved into the familiar pyramid shape. Khufu's pyramid, known also as the Great Pyramid, was one of the 7 wonders of the ancient world and is the only one remaining. Weighing 5.7 to 6 million tons, originally 147 metres high and with a base length of 230 metres, the pyramid was the world's tallest man-made structure until Lincoln Cathedral was built in England about 3,800 years later. Although hieroglyphs depict many aspects of life in ancient Egypt, none illustrate pyramid building. The absence of documented evidence means that the technique used to assemble the pyramids is a mystery, although many solutions have been proposed over the years. The assembly problem that faced the ancient builders is the same problem that faces us now, and so the aim is to find the same solution they found by logical inference, basic physics, and a knowledge of the contemporary practical constraints. The wheel and axle had yet to be invented, iron and steel were unknown. Only stone and copper tools were available at the time. The pyramids have puzzled and amazed many down the centuries, including the Greek historian Herodotus, who visited Egypt circa 440 BCE, when the necropolis was already 2,000 years old. Like many a traveller since, he was staggered by the sheer scale and asked locals how the ancients constructed them. They answered that the pyramid builders used machines to help them. If true, the Giza pyramids were not built by brute force, the traditional method employing perhaps 80 to 100,000 slaves, but were assembled using a far more efficient technique. Indeed, archaeological evidence discovered quite recently implies that the pyramids were built by a well-fed elite, numbering just a few thousand. The modest size of the workforce, perhaps totaling no more than about 10,000, is itself an indication that the informants of Herodotus were probably right, since a relatively small assembly team would need to use machines if they were to complete the huge project on time in about 20 years. It was imperative for the ancients to try and complete construction while the pharaoh was alive so that he could view the finished work. It was therefore necessary to proceed quickly. The vast scale of the task and the need to finish as soon as possible meant that a key question was, what is the fastest practical way to assemble the pyramid? The pyramids are built to high precision. An internal construction technique would involve very difficult surveys and run the risk of distorting the pyramid's overall shape. To maintain an exact shape without performing complicated surveys, it would make sense to build the pyramid one layer at a time from the outside, using the very accurately surveyed base layer as reference. An important hint as to how Giza's pyramids might have been assembled using simple machines can be found inside the Great Pyramid itself. The crucial clue, a portcullis, shows that the ancients understood the use of counterweights, and so they probably invented a machine employing the counterweight principle. The builders knew that many small weights combined can lift a much larger weight, knowledge that probably led to the idea of a gravity engine, so called here because gravity does the heavy lifting. Gravity engines had to be simple, robust, reliable, and easy to use, and made of materials available in Egypt at the time. But first we need to consider how stone blocks were transported from the quarry floor up onto the top of the Giza plateau, about 30 metres above the Nile Delta. The sketch shows how stone blocks would have been transported from the quarry floor to the top of the Giza plateau. The golden rule for moving anything very heavy is not to lift it but to slide it. The stone blocks can easily be slid on a flat horizontal pavement covered in liquid mud. This has been shown to be achievable by a relatively small team of workers. We can see that in order to raise the block onto the plateau, a new method is needed. This technique was discovered by archaeologists quite recently in another part of Egypt. A rope is placed around the back of the block and over a pair of securely fixed wooden posts either side of a ramp. Two teams of workers pull on either end of the rope, which tightens and forces the block a little way up the ramp. The block is then pegged in position and the process repeated a second, third, fourth, fifth time until the block reaches the top of the plateau. But this method could only be employed on slopes of no more than about 20 degrees. It could not be used to assemble the pyramid itself, whose face slopes at an angle of 52 degrees to the horizontal. Once at the top of the plateau, the block is then placed again on a flat horizontal pavement covered with liquid mud and is dragged by a team of workers the roughly 0.7 kilometres to the pyramid's base. Having delivered the block to the base of the pyramid builders now face the problem of how to get this 2.5 ton block up the face of the pyramid, which is at an angle of 52 degrees to the horizontal, far too steep for them to drag it by any conventional method. And this is where the gravity engine was introduced. This is why it was necessary to invent a machine to help the pyramid builders. There are approximately 2.3 million blocks inside Khufu's pyramid. Blocks at the base of the pyramid are much larger than those at the top, and about 500,000 tons of mortar was used to infill within the pyramid because blocks within the pyramid aren't carefully cut like those that we can see here on the outside at the base. They're much more rough hewn, and so it required mortar to infill them to hold them together. The following schematic diagrams illustrate the principle of the gravity engine. Schematic of a gravity engine not to scale. Key components of the gravity engine are one strong cylindrical roller, two very sturdy supports, two long pieces of strong rope, two identical wooden sleds on runners capable of carrying several tons each, wedge-shaped stones having two parallel grooves, sandbags, lubricant, and a team of porters. 1. Two very sturdy supports having well-lubricated sockets are firmly fixed at the top of the pyramid face. 2. A very strong cylindrical roller is located in the sockets. 3. In the starting position, one sled is at the bottom of the face, the other is at the top. Strong rope is attached to each sled and to the roller. 4. Two tracks, one for each sled, are laid on the pyramid face. The tracks consist of wedge-shaped stones fixed in the steps on the face of the pyramid. Two grooves are cut down each track. The grooves receive the sled's runners and are filled with lubricant. The grooves keep the sleds moving in a straight line. 5. Initially, a block is loaded onto the sled at the bottom via a shallow ramp. 6. Sealed sandbags, ballast, are passed by a chain of porters up steps on the pyramid face and loaded onto the sled at the top. 7. When the weight of ballast overcomes resistance, the top sled starts to move down the track, rotating the roller, thus raising the lower sled with the block. At the top of the pyramid face, the block is removed from the sled and slid on a lubricated horizontal surface into its final position in the pyramid. 9. When the ballast carrying sled reaches the bottom, the sandbags are removed and replaced with a fresh block. The sandbags are then passed by porters to the top of the face and loaded onto the empty sled, and the process repeats. 10. When the pyramid reaches a certain height, determined by the length of the strongest rope available, a new phase of construction begins in which gravity engines are used in 2 or more stages. The elevation view of the gravity engine shows how the wedge stones are fitted into the steps on the pyramid face. We also see the grooves cut in the wedge stones that will take the sled's runners and the lubricant. Comparing work done against friction, ramp versus gravity engine. The efficient use of energy is key to building the pyramids quickly. The main energy waste in both cases is due to friction. The total energy expended, also known as total work done, lifting a block from ground level to the top of a slope is total work done equals work done against gravity plus work done against friction plus energy of motion of the block, kinetic energy. The kinetic energy, which equals a half the mass times the square of the speed, is relatively negligible. So to a very good approximation, total work done equals work done against gravity plus work done against friction. It doesn't matter which route the block is taken up the ramp. The work done against gravity is the same. So when comparing the two methods for energy efficiency, the differentiating factor is the work done against friction. In general, work done against friction equals friction times ramp length, where friction equals coefficient of friction times weight of block times cosine theta, where theta is the ramp angle. Work done against friction equals coefficient of friction times weight of block times cos theta times ramp length. Comparing the work done against friction, the key factor is cos theta times ramp length. Assuming coefficient of friction is roughly the same for liquid mud and the gravity engine's lubricant, and that the block's weight is the same in both cases. So, the efficiency ratio is S cos theta over D cos alpha, where S is the length of the ramp slope, theta is the angle of the ramp, D is the length of the slope in the gravity engine, and alpha is the angle of the face of the pyramid. So theta equals 7 degrees and alpha equals 52 degrees. Hence, the ratio is approximately 1.6 times S over D. If, for example, the vertical height above ground level is 50 metres, S equals 410 metres and D equals 63 metres, giving a ratio of 1.6 times 410 over 63, or about 10 to 1. However, this ignores friction at the cylinder. If the total friction at the cylinder ends is comparable to the total friction at the sled's runners, the ratio would halve to about 5 to 1. However, rolling friction at the cylinder ends is generally less than sliding friction. Therefore, the true ratio is probably between 10 to 1 and 5 to 1. So, the gravity engine is much more energy efficient than the ramp method, saving cost and time. It should be pointed out that the reason the ramp angle is 7 degrees is that beyond that angle, at larger angles, it becomes increasingly difficult for a team of workers to drag a heavy block up a ramp, and it's generally assumed that 7 degrees is about the maximum angle that's achievable with that technique. The ancient Egyptians were a practical people, so I think it's very unlikely they'd advanced mathematical analysis to find out which was the better method, the ramp method or the gravity engine. Instead, they would take the view that the easiest way to discover which was better was to have a test, an experiment, in which they had 2 teams of workers. One were to drag a block up a ramp, and the other were to use the gravity engine. And all of the factors being equal, they would compare the 2 methods in practice to see which was the most efficient at delivering blocks up slopes. Now, it's possible that in the very early stages of the pyramid, the first 2 or 3 or 4 layers, the ramp method might be quicker, but at some point, fairly early on, the gravity engine will become the most efficient way to build the pyramid, and I'm fairly sure that's what they discovered. However, we could still do the experiment today. This could be tried out now, just as they would have experimented 4,500 years ago, to find out which method works best. Comparison of ramp versus gravity engine, energy efficiency, a worker's perspective. Each time a block is delivered into the pyramid by ramp, each worker must climb the full height of the pyramid face from ground level, as the diagram shows. The work done, W, by each worker in raising their body through height h is W equals mgh, where mg is the worker's weight. Weight equals mass times acceleration due to gravity, i.e. mg. And h is the vertical height of the pyramid face. In the case of the gravity engine, it would be unfair to make the same worker climb all the steps every time to the top. So the workers would circulate such that the worker at the top of the face would go to the bottom and the rest would move up 1 step each time a block was delivered into the pyramid. Hence, each worker would occupy every step on the face once over a complete cycle of n blocks, where n is the number of steps. So this makes it fair. Every time a block is delivered into the pyramid, each worker raises their height above the ground by 1 step. Clearly, 1 step equals h over n. Hence, the work done per block by each worker in raising their body weight by 1 step is W equals mgh over n. So, by comparison with the ramp, W equals mgh, the gravity engine is n times more energy efficient per block per individual worker. Another reason to prefer the gravity engine over the ramp method. But another factor in deciding which of the two methods is better is that every time we change from one layer to another, and there are 210 layers in the pyramid altogether, then when you use the ramp method, you have to raise the ramp by a corresponding height. Now, the height of a particular block is about 0.7 meters. So you've got to add all that extra soil and infill on top of the layer of the original ramp to take you up to the next level. That would involve a considerable amount of work, particularly as the ramp gets a lot bigger. And that's going to slow you down because you can't load blocks into the pyramid when you're doing that alteration work. By contrast, with the gravity engine, every time you go up a new layer, you've only got to add in those special wedge stones to take you up to the next level. And that takes no time at all by comparison. If you add the total time wasted over 200 different layers, then using the ramp method adds considerable time to the building of the pyramid. Since time is the key factor in building the pyramid, we're trying to build it as fast as possible, this is a major argument against using the ramp method. This drawing shows a huge statue that's being pulled along by a team of workers. There are more than 130 of them depicted here, pulling on a rope. This rather suggests the ancients were able to make quite long ropes, maybe 150 to 200 feet long. If so, that means that a gravity engine may have a range of about 200 feet, which is roughly half the height of the Great Pyramid. So the thesis is that the pyramids were built in 4 stages. First of all, a simple ramp to assemble the first few layers with the very big blocks in, perhaps the first 4, 5, 6, 7 layers. And then the gravity engine was used for the next roughly 200 feet. And then after that, at about maybe 250 feet above ground level, a second stage gravity engine was used to take blocks from that point to close to the top of the pyramid. The question then is, in the 4th stage, how was the very top of the pyramid assembled? This sketch, which is not to scale, is just a schematic to illustrate how the top part of the pyramid might have been constructed. By the time we get to the nth layer, it's no longer possible to use gravity engines beyond that point because they simply won't fit because there isn't enough space. So the idea is that a scaffold is built on top of the nth layer, as shown there. And the idea is that slabs taken up to the nth layer are attached by a rope, which the other end of which is attached to a counterweight and one of the workers A. The counterweight helps A lift the slab. A second worker B has a rope attached to the slab and is able to pull and maneuver the slab sideways. So between the two of them, A and B, can raise and lower the slab and can move it horizontally as well. And that's how the slabs can be located into position and how the top part of the pyramid can be built in that way. The pyramidion itself could also be positioned using that technique. With regard to the pyramid's facing, it is possible that the Tura facing stones were located as the pyramid was being assembled, bottom up rather than top down. The facing blocks would be raised using gravity engines and placed like curbstones around the perimeter of the particular layer of the pyramid. Summary. 1. The pharaoh hoped to live long enough to see the project finished, so the pyramid had to be built as quickly as possible. It was therefore necessary to find the fastest, most efficient way to proceed. 2. It was essential that the pyramid retain its precise shape. To make surveying as accurate and as straightforward as possible, the structure was built one layer at a time from the outside, with the very accurately surveyed base layer acting as reference. 3. The first few layers would probably have been built using a simple ramp. At some point early in the construction, the ramp method would become inefficient and time-consuming, and so a more efficient, faster method had to be employed. 4. The quickest way to locate a block inside the pyramid is to go straight up the pyramid face and straight to the final position. Hence the big question, how to transport a 2.5 ton plus block up an incline of 52 degrees. The builders left a portcullis inside the Great Pyramid, and that proves they understood the concept of counterweights, using many small weights to lift a large one. 6. Based on the counterweight principle, the builders constructed a simple machine that I have dubbed the gravity engine, as gravity does the heavy lifting. 7. Because the gravity engine is easy to make, several could be located on the pyramid's faces. With, say, 4 machines on each face, it can be shown that each had to deliver 2 blocks per hour in order to reach the required target of 1 block every 2 minutes, the average rate needed to build the pyramid in about 20 years. Of course, with 8 machines on each face, any given machine would need to deliver only 1 block per hour to reach the overall target rate, a demand which would not require superhuman effort if there were about 100 porters per machine. 8. When the rope reaches a certain maximum length, 150 to 200 feet perhaps, the gravity engines must then be used in stages. The pyramid face is about 600 feet long at maximum, so 3 or 4 stages would be required altogether. 9. Near the top of the pyramid, space is at a premium, and the gravity engine can no longer be used. A wooden scaffold is then erected on top of the top layer, the nth. Slabs of stone are then sent by gravity engine to the nth layer. The slabs, smaller than blocks lower in the pyramid, are then lifted using counterweights attached by ropes and rollers to the scaffold and placed in position to form the n+1th layer. In the same way, n+2, n+3 layers are built until the area of the top layer is equal to the base area of the pyramidion, the capstone. 10. Finally, the pyramidion is lowered onto the pyramid's top layer, and the last workers descend from the top of the pyramid by steps left on the pyramid face, filling the space behind them with concrete made from limestone. NB. At 60 tons each, the largest blocks in the Great Pyramid are in the roof of the king's chamber. Those huge blocks might have been located using a set of gravity engines inside the so-called Grand Gallery. Finally, as the physical evidence shows, the builders of the Giza pyramids were a well-fed elite. This suggests that those in charge of the project understood that fit, healthy and happy workers are likely to be much more productive than injured, starving workers under the slave master's whip, and high productivity was key to building the pyramids quickly. As a final comparative point, if the pyramids were built using some kind of ramp method, as these diagrams illustrate typical ramp designs, then we can see that building the pyramid using really any sort of ramp involves two huge projects. The building of the pyramid itself, but also the building of the earthworks and the ramp, all of which had to be dismantled at the end. So in pursuing this method of pyramid construction, you're in fact giving yourself two very big projects, the building of the pyramid and the building of the earthworks and the ramps. And that's why I think that using the gravity engine, which clearly only really involves one major project, that's to say the building of the pyramid, and this would have been, I would have thought, obvious to the ancient Egyptians. So, a summary of the key advantages of the gravity engine method over the ramp method. In the case of the gravity engine, 1. There is far less energy and time spent building and disposing of ramps. 2. Much less time wasted going from one level of the pyramid up to the next. 3. Much less energy wasted overall due to friction. 4. Much less energy used per worker per block. Given the choice, if you were a porter working in an assembly team, which method would you adopt? That's the end of this video. The next one in the series will be concerned with missing Malaysian flight MH370. So look out for that one, and thanks for watching this video.